Thanks. So, hello everyone. I'm very pleased to talk about our research about bringing the WebAssembly standard up to speed with SpecTec. And I'm the presenter, Dongjun Youn. So here is a short recap about the WebAssembly. WebAssembly is a lower-level code format designed for efficient execution, especially on the web. For example, if we have a C code like this, then this is translated into a Wasm function like this. The computation model of WebAssembly is based on the stack machine. So when we execute the burst instructions local.get and local.get1, then we push the two parameters x and y into the stack. And when we execute the i32.add, this pops two values from the stack and push new values into the stack. In order to mitigate the risk of the implementation divergence, WebAssembly requires 4 artifacts for a new feature to be standardized. First, we need a formal specification, which describes the behavior of WebAssembly in a declarative manner. We also need the prose specification, which describes the behavior of WebAssembly in an algorithmic manner. We also need the reference interpreter, commonly written in OCaml, and we also need the test suite. So basically, we need so many artifacts like this. And this imposes several challenges. First, it's very laborious. All of the documentation and the maintenance should be done in a manual manner. Also, it shows the bad readability, especially for the specifications. They are written in LaTeX or restructured text, and code reviews for them make it very un-user-friendly. Also, this process is very error-prone. The correctness of the artifact itself or the consistency within each of these artifacts should rely on the human eyeball correspondence. Long story short, we definitely do not want to write, review, or maintain this bunch of complex code. So this brings us the question, can we do better? And the answer is yes, using our new suggested framework, SpecTec. SpecTec is a framework for mechanizing the specification of WebAssembly, embracing both algorithmic and declarative styles of semantics. It provides the domain-specific language, DSL, which can easily describe the syntax, type system, and the execution semantics of WebAssembly. The definitions written in this DSL can be used as a single source of truth from which all of the various artifacts can be automatically generated. Here we have the high-level overview of the structure of the SpecTec. First, we have the backbone of the SpecTec, which consists of the DSL input and all of the intermediate representations, from which multiple artifacts can be generated as a backend. Let's start by looking at the first step, the translating from DSL into EL. So first, we have designed the domain-specific language, DSL, which can concisely describe the Wasm WebAssembly specifications like syntax, typing rules, execution semantics, or the functions. Especially, this design is closely resemble the pen and paper notation commonly used in literature. So for example, you can see the typing rule has a turnstile, which is described using the vertical bar and a hyphen. Then the definitions written in DSL is parsed into a language we call external language, or EL. Here we have the excerpt of the syntax of the EL, and you can see the top-level definitions here, which consist of syntax, various relations, function definitions, or the variable declarations. Next, what we do is we transform EL into a language called IL, and we call this process elaboration. The purpose of this process is to make the EL into a more explicit and unambiguous language. During this process, various things happen like type checking or dimension inference. if you look at the code left, it fails to type check. And if you see at the code at the right, it succeeds at the type checking, and also it infers the dimension of the variable x and y by looking at the list x star and the list y star. Next, we have some internal transformation from IL to IL. Again, the purpose of this process is to make it even more simplified and more explicit notations. Various things happen during this process, including inferring the implicit side conditions. For example, when you have the last premise there, if x is smaller than y plus 1 star, that implies that the length of the variable x star and the length of the variable y star should be equal, which is already implicitly inferred. Then this implicitly intercite condition is automatically injected as a premise. And finally, we have the transformation from IL to AL. And here, AL, the algorithmic language, represents the runtime semantics of WebAssembly in an imperative algorithmic style, from which prose and the interpreter backend can be easily generated. For example, here is the excerpt of the syntax of AL, and you can see that the push and the pop statements, which corresponds to the push something to the stack or pop something from the stack, you can see in the prose specification. Translating IL into AL is mostly straightforward after we have done some pre-processing. So let's say we have the pre-processed IL there, which consists of LHS, RHS, and a bunch of premises. Then this can be straightforwardly translated into AL simply by pattern matching on each of the sides. So the main challenge now lies on each of the pre-processing step. The first pre-processing step is what we call the anti-unification of LHS. If we have two different reduction rules for one WebAssembly instruction and the left-hand side of them are different, then they should be anti-unified, or which means they should be merged into the same format. For example, for the WebAssembly BR here, the one rule of the LA1 rule has the left-hand side BR0 and the another rule has BRM plus 1, then this should be anti-unified into the BRM, and the appropriate premises should be injected as a consequence. Next pre-processing step we do is the identification of binding occurrence. The goal of this process is to identify whether each of the equality premise in the IL is a binding occurrence or an equality checking, so that each of the variable is bound exactly once, if that is possible. We solve this problem by reducing this problem into a problem called exact cover problem, whose goal is to find the pairwise disjoint sets whose union is the entire set. Here's how it works. First, each premise is encoded into a collection of a specific sets in a certain manner. For example, the first premise here is encoded into two sets, 1A, B, or 1. And this means that, for example, if the first set 1AB is selected, then the first premise binds two variables A and B. Next, we find the exact cover from this collection of sets using the well-known algorithm called QNIF algorithm. For example, when we find the exact cover of 1, 2, A, and B, here the result is the 1AB and 2, and this implies that the variable A and B are bound by the first premise, while the second premise does not bound any variable, meaning the second variable was in fact the equality checking. So now we have the backbones of the SpecTec with multiple representations. We can generate various artifacts as a backend. Currently, we generate 3 backends: the LaTeX backend, prose backend, and the interpreter backend. So first look at the formal LaTeX and the prose backend is generated. For input, we need 2 things. First, we need the skeleton code that will be spliced later, and we also need the specification of WebAssembly written in DSL. This definition is pre-processed into the AL and EL respectively, and will be rendered into this bunch of complex code again. Thanks, we don't have to manually write all of this. This is automatically generated. Now, this is now rendered into the PDF document in PDF or HTML like this. Next, we have the indirect interpreter. Here, this interpreter is indirect because we want to interpret the WebAssembly by interpreting the specification, which is written in AL. AL is also a language that has its own semantics, so we can have the interpreter for AL, which means when we have the specifications of WebAssembly written in AL and the interpreter of AL, the combination of whole thing work as a WebAssembly interpreter, which can input a code, Wasm code, and returns the result of the expected behavior like this. We evaluate the SpecTec in terms of 3 criteria: correctness, bug prevention, and the forward compatibility. First, we show that SpecTec could correctly and automatically generate the formal and prose specification for WebAssembly 2.0, which is the current version of WebAssembly. And also, it could automatically generate the indirect interpreter as well, which show the 100 pass rate for all of the applicable official test suite. Next, in order to show the bug prevention capability of the SpecTec, we injected 13 retrospective spec bugs that actually happened during the spec development into our spec definitions written in DSL and run the SpecTec. As a result, all of the bugs were detected at various phases during the SpecTec, including type checking or executing the test suite. Finally, we showed that the SpecTec is a forward-compatible tool. SpecTec could handle the 5 proposals to be included in Wasm 3.0, and during this process, we also found and reported 10 more bugs that were in the proposal. This furthermore showed that the SpecTec's capability in terms of catching and preventing the bugs of the specification. So in summary, we presented our new framework SpecTec to bring the WebAssembly specification standard up to speed with SpecTec. SpecTec is an open source project which is available in the QR code here and the link there. And this project tries to automatically generate various artifacts from the given DSL. Thanks for listening, and I'm glad to hear more of the questions. Thank you.
Okay, we have time for perhaps one question. Do you have a question? Yeah, go ahead.
So, first off, thank you for freeing us from Bike Shed. Really happy to see that. Maybe Tab can take some inspiration from this, you know, just saying. CSS, if you're hearing me. Anyway, question though, how does this, does this work with things that maybe interface outside libraries like the JavaScript API spec kind of thing that we have, which is sadly riddled with bugs? So that's a question.
Yeah, currently WebAssembly is a bit specialized for WebAssembly, but I believe that it can be easily extended to express the outside specifications like JavaScript, and I think that's possible.
Oh, I didn't mean the ECMAScript spec. I meant the JS API 2 spec that we have for Wasm.
Okay, I'm not sure if that would be, okay, I think that would be possible, but I'm not sure. I cannot give that definite answer for now. But
Thank you.
yeah.
Hi, thanks for the talk. That sounds very cool. I was gonna ask about, like, the obvious thing seems to be to do something with regards to extracting this to theorem assistance. Now that I'm closer to the slides, I see that it's already on there. You just didn't mention it. So can you say a few words about apparently the thing you already did but didn't have time to cover in the talk?
Oh yeah, so I cut some of these contents for the time. So anyway, so yeah, there are two more backends that we're planning to do. The fuzzer backend, which generates the WebAssembly test automatically, which is currently in progress, and we currently in a distant state for it can. It is currently in distant state that can automatically generate some various WebAssembly tests. And we are also planning to do also the prover backends, which automatically generate the mechanistic proof for the WebAssembly standard, and we're planning to work on them soon.
Oh, so that's still work in progress. Okay, cool. Thanks.
Thank you.
Okay, let's thank our speaker again.